Okay. Hi guys, my name is Justin Dye.
My name is Daniel.
I'm Lucas King.
I'm Darren Ham.
And this is our team name is the Beatles, and this is our autonomous rover.
Our objective is to construct and code an autonomous rover in 2 weeks that can fully navigate a course with the predetermined goal, which is to move along the track and to pick up and identify a red can. The design decisions, 65 millimeter wheels for its sturdiness and grip, with better stability for the rover. 34:1 gear ratio for better speed, since the rover won't be that heavy. Modified T chassis for better stability, weight, and simplicity to attach the claw design. And the sliding claw, which is a more original idea based on the name of our rover.
All right, so for our build decisions, we decided to go with the T chassis that was already provided, and we decided to make it out of wood. We also added a couple modifications just to make the install of our custom claw bit easier and just installation overall. The design made it easy to operate on and also made it light and pretty sturdy as well. And the claw, again, original idea and inspired our team name.
For our testing, so when we tested our rover, one of the problems we encountered was the rover not moving due to encoding issues. It was because that we coded the rover to move when it detected black with the iris sensors, but in reality, we had to make it detect the white and move in the straight line. And another issue we faced was that our rover stepped on, so we had to rebuild the whole thing.
And for the algorithm portion, there were two modes. So there was the line tracking mode and the color tracking mode. For the line tracking mode, there are two sensors on the front of the rover, and when both of these sensors detect white, the rover will move forward. When one of them detects black, one of the wheels will stop, which will pivot, which will allow the car to pivot. And when the other sensor detects black, it will cause the other wheel to stop. When both of those sensors detect black, it will switch into the color tracking mode, which will activate the camera or the pixie cam, and it will track the color red, which is the color of the can, and it will drive towards the can. And once the color is large enough width on the screen, it will close the claw, which will achieve our goal.
For our schedule, on days 1, 2, and 3, we did on-chip Arduino code and electronics practice. On day 4, we did our design decisions, and we started working on our on-chip claw. Day 5, we finished our on-chip claw design, and we started working on our chassis. Day 6 and day 7, we still completed the chassis, and we started working on Arduino code. On day 8, we did bug fixings, especially on the iris sensors and pixie cams. And on day 9, we finished the poster and all the rest of the bug fixings. Day 10 is presentation.
So overall, in conclusion, we felt that our rover met pretty much all the requirements and did so pretty well in a pretty creative and interesting way as well. Throughout this whole experience, we had many different tours throughout the campus and lectures from the different UAs and teachers, which really enhanced our knowledge and experience of college and industry life here. So we felt that it was a pretty satisfying experience overall.
Thank you.
All right. Hello everyone. Our team name is the Chuds, and I'm Benny.
I'm Ryan.
I'm William.
And I'm Daniel. Jen.
All right. So for this project, our objective was to build a custom fully autonomous rover, which functions using an Arduino board, PixieCam, eye sensors, as well as 2 motors and a servo. Our project goals was to have the rover successfully follow a black path on the ground through line detection, and then pick up a red can at the end with object detection and our PixieCam.
So for design decisions, we decided on wheels that were vertically smaller but wider to get more surface area for better grip, and we used the 34-to-1 motor in order to have the rover move faster because it had a higher RPM. And then we chose the chassis that was wood and also was like T-shaped in order to like have it be more firm. And we used a claw design with 2 gears, one connected to the servo and one connected to the second claw, so that the claw would open on both sides. And then for the build, we used an Arduino board, 3D printed claw mechanism, servo, battery, a wood chassis, motors, wheels, and a resistor. And we first assembled the electrical part by like soldering, and then we mounted it to the chassis.
All right. We repeatedly tested the rover by running it through the course to get its line detection algorithm working. And through that process, we discovered that the IR sensor spacing actually plays a big role in how it like functions on the track. So in order to solve that issue, we like played around with the physical dimensions and stuff until we found something that worked. Another issue we encountered was with the claws, where we had to redesign and completely reprint them because the gear teeth were spaced wrong when we printed it. So that was an interesting issue. And finally, we had to rework the object tracking through our PixieCam, which took a lot of debugging and like iterational stuff with our code. All right, Daniel.
So as for our algorithm or code, it's separated into 3 parts: line detection, as mentioned before, object and color detection, and grabbing. I'll start with line detection. There are, as mentioned by like the other groups, we have 2 IR sensors. Like the other groups, we have 2 IR sensors, and there are essentially 2 values that can be assigned to them, sort of like a Boolean, but like it's an integer. It's 0 and 1. It's 0, it's off. It's 1, it's on. It detects something. It detects black, and this dictates how the rover moves. So like if neither sensor detects anything, it moves forward. If both sensors detect something, it stops, and then it runs the get object function. And if only one IR sensor detects black, then it will move either right or left. As for the actual object detection and line detection itself, we used methods attached to like an object in an array list that's stored in the PixieCam array list. And like what these methods do is that it returns certain stuff like the coordinates of the rover, the width of the rover, etc. And we used these values to adjust the rover's position / movement based on like the can's position once it has stopped. And for the claw, it's really simple. We programmed it in such a way that like when like we started, like it just opens immediately, and like for the when like the can is close enough / or like the width is like small enough, large enough, aka it's close enough, then it will just snap shut. So yeah, that's how it works.
So during the day 1 to 3, we focused on learning the fundamentals of the project. We became familiar with the project requirements and learned how to use the Onshape for CAD design. And we also practiced Arduino programming and gain. From days 4 to 6, we moved into the design and assembly stage. We finalized the rover, selected our stage. We finalized the rover's design and selected our components and soldered the electronics and assembled the chassis and started programming the rover. And during days 7 to 9, we focused on testing and improving the rover. We fixed electrical issues, debugging our code, and tested the rover on the track. And we made adjustments based on that and prepare our presentation poster, which is for today. And today, finally on then day 10, we're giving our final presentation and demonstrating the results of our projects. And as the conclusion, during the process of building our rover, we discovered that multiple iterations are often necessary to reach our final goal. For example, the claw required a redesign due to issues that we didn't consider until the prototype was printed. We also learned a lot about coding C++ on Arduino through the process, making many changes to the code as we tested to find a solution. In the end, we're pretty satisfied with how the rover turned out and our hard work paid off.
Thank you.
Hey everyone, my name is Jane.
My name is Caroline.
I'm Allison.
And we're Team Posh. So, autonomous rovers are designed to navigate and complete tasks without any direct human control. So, in our autonomous rover project, we used IR sensors to detect the black line on a white background, a pixie cam, and a claw mechanism to identify and grab a can at the end of the course. So when it comes to our design, we used a 34-to-1 metal gear motor, which provided higher speed and lower torque. Our 65mm wheel helped us bring stability and precision as well as smoothness. Our double-layer rectangular chassis optimized maneuverability, and the 2 layers prevented wire entanglement. The triangular arrangement of the sensors, the IR sensors and the motors helped us with balance and precision, and our claw design with a stationary and moving claw, creating a circular shape when it comes together, helped us securely grasp the can.
So I'll just briefly go over the specifications on this. So my rover has 4 main parts: the chassis, which is the basic structure. It has 2 wooden laser cut layers. First one is like a 6-by-inch circular square, and the bottom 6-by-8 inches. And then the second part is the claw mechanism. These have a 1.3-inch radius, so it can tightly grasp the can. And then the moving claw is on top of a 5mm servo, which allows it to rotate. And there's also a buck converter, which reduces the voltage that goes to the servo. And then there's also the driving mechanism. So Jane has gone over the motor and the wheels, but there's also a caster ball at the bottom, which is a support. It's kind of like the front of a tricycle. And then the final part is the sensors and electronics. There's 2 infrared line tracking sensors over here that differentiate between the white and black on the track. And then there's also a pixie cam vision sensor, which kind of just lets the rover see. And there's also an Arduino board, which is wired to all the components, and the code gets uploaded to it.
Okay, so now I'll explain how.
So for testing, we just did multiple trial runs and revised them on the way. So the first issue is just that the left motor was spinning kind of backwards, so the rover couldn't really move forward. So we just reversed the wires. Another issue was the alignment. So our rover, when it moved forward, it kept bumping into the can with the claw over here. So to amend that, we kind of just shifted the coordinates of the pixie cam in the code. And then we also rotated the the stationary claw a little towards the side. So this prevented this thing from bumping over the can.
Okay, so now I'll explain how we are actually able to program our rover. So there are three main steps. First, line following. We use two IR sensors underneath the rover to detect the black line so the rover could be able to follow it autonomously. And based on the sensor readings, the rover and Arduino would adjust the speeds of our left and right motor. So when the speed of the left and right motors are different, the vehicle is able to turn, and when they're the same, the vehicle would move in a straight line. The Arduino would continuously make these small adjustments, allowing the rover to accurately follow the line until it reaches the end of the course. After it reaches the end, this initializes the second stage, which is object detection, where the Pixie Cam searches for the can used by its programmed color signature. The Arduino uses the can's position in the camera's view to adjust the motor speed and rotate the rover until it reaches the correct alignment. Initially, we programmed the rover to perfectly center the can in the center of the camera. However, we discovered that when the can was actually centered, the claw would hit the can instead of grabbing it. So to solve this, we had to change our alignment target so the can was slightly off and could actually grab, so the claw was slightly off and could actually grab the can. We continued to fine-tune the motor speed values through repeated testing until the rover could consistently approach the can from the correct position. Finally, for object grabbing, the servo-controlled claw opens the rover as it approaches the can, and once the can is within range, the servo rotates to close the can around it. Over the past 10 days, we designed, built, and programmed our autonomous rover. We all learned CAD, Arduino, assembled the hardware, developed and debugged the code, and refined the rover repeatedly through testing before now presenting our final project. Although each of us as team members had different responsibilities, we always consistently communicated, shared ideas, and made decisions together. Whether we were debugging the code, redesigning parts, or testing the rover, everyone contributed to solving problems as a team. Thank you.
Thank you to the rover team for the wonderful presentation. So we're going to go ahead and go into the Lab on a Chip presentations now. So could I get a volunteer from Lab on a Chip to go first? Okay, you guys, great. Second. Okay, over there, I saw them first. And then third for Lab on a Chip will be the last team. Yes, yeah. Okay, thank you guys. So let's go ahead and... All right, who was first again? You guys? Okay.
Okay, hi everyone. This is the Deep Seekers Dry Eye Disease Detection Project. My name is Brian and I did the chemical part of this project.
My name is Shini, and I did the biomedical part.
My name is Jackie. I'm the electrical.
I'm Amy. I was also responsible for biomedical.
Okay, so our background is in optometry. Fluorescein solution is used to detect dry eye disease. When the solution is placed on the eye, a doctor shines a blue light to the damaged cells so it'll glow bright green. In the project, we try to combine a PDMS chip with electronics like Arduino, LED, and sensors to find out and determine the concentration of the fluorescein solution.
Right, so now moving on to design decisions. So this is what our Lab on a Chip looks like. And well, the box, it's an 18 by 18 by 18 centimeter cube, and it's green, but we painted the inside black, as you guys can see, because our device detects green, and we don't want that to interfere with our results, so we painted it black. And then we also have this, I don't think you guys can see this, but we have a little shelf thing on the inside to hold the tray, so it stays like in the middle. And then on the side here, there's two holes. This one is for the cable to come out, and then this one is for us to look into the box to see the LED lights.
Okay, so for the build, as you guys can see, it's a 3D printed house. We got this house from the design from Onshape or CAD, and there's two layers to this house. The first layer is the wires, the LEDs, the Arduino, the breadboard, And then the second layer is where the Arduino and the RGB sensor are. And one of the most important parts, especially on that first layer, was the tape, and to basically hold all the wires together and make the circuit tidy, and overall just make the whole thing consistent.
So for the test, I guess you are pretty curious about the process, how we did it. So I'm going to explain it really quick, briefly. So we mainly use syringes and pipes to conduct our calibration. So as you can see, there are some pipes coming out from the box. We use the syringe to push the our sample, the fluorescent, slowly into the channels and wells. And we have to be really careful because the channels are really tiny. They're like in micros, yeah. And luckily, there was no gray leakage. We can deal with it. We're really lucky. So when the fluorescent passed through the channel and to the detection well, the RGB sensor above the well will detect the color and give us feedbacks, like they gave us RGB values that we can use. And then we just repeated the same steps, but with different concentrations from 250 ppm to 1000 ppm for several times. After that, we got a lot of data to use. We can then derive the relationship between the concentration and intensity, as the equation and graph show here. I equals 0.02 C plus 61. Here, the I is the intensity, or how green it is, and the C is concentration of the fluorescein. All right, let's take a look at our algorithm. There are three main parts or steps in our code. The first one is the setup. We make the Arduino, the green board, to recognize our devices. For example, the LEDs are outputs and the sensor is an input. And next, we tell the RGB sensor to convert the color it detects into the RGB values. And finally, the LEDs are controlled to be on or off based on these values. And then we can determine the approximate concentration of the sample. This is generally how it works.
Right. Now we can talk about our timeline. So in total, we had 10 days, including today, to work on this. And then for the majority of the first week, we spent a lot of our time just getting familiar with the stuff, like the basic stuff, like Onshape, Arduino, etc. And then we started on the actual building, design, and coding towards the second half of the session. So we completed most of the coding and assembling of the circuit stuff on day 6. And then we did most of the CAD and then the printing and stuff on 7 and 8. And then we did a lot of our testing and stuff yesterday.
So once we finished printing our box, they gave us a mystery concentration solution for us to find out the concentration, and we did that pretty accurately. So I would say that our box is constructed quite well. And overall in this project, we've learned many skills such as computer science, chemistry, time management, and teamwork. And I feel like most importantly, the teamwork is the most important part because each member plays an important role based on their strengths. Like some people knew how to code, some people knew chemistry, etc. And once we combined those skills, we managed to make this box. And I feel like these skills that we learned will be pretty useful in our future studies and careers. Thank you.
Hi guys. Okay, so yeah, I'm using Vulkan for Lab on a Chip. I'm Billy.
My name's Eric.
I'm Michael. I'm gonna introduce the background first. So the problem for the dry eye disease detection right now is still relies on people to judge by eye. However, many observation can be inaccurate because different lighting condition can affect how the colors look. So our goal is building a lab-on-chip color detection system. The system is designed to measure the concentration of a sample by detecting color intensity using an Arduino board and color RGB scissor and LED light. And
So
that's what we make.
Oh, yeah, okay. So I'm just gonna quickly talk about the design of the box. And for those of you who have played Minecraft, you will know that this is a command block. You might be wondering why we made a command block. Well, inside, which I'm gonna open now, you can see that there is an Arduino board. And essentially what it does, it controls the home press system using coding in C++. And that's basically what a command block does in Minecraft too. Additionally, in here we have the chip and a breadboard which controls all the wires. And if you look around the box, you will see at the top there are 3 holes for the tubes going into the chip, 8 holes outside for the red LEDs, which signify the intensity of the concentration. And at the very side, there's a cable leading that's supposed to be plugged into a computer, but it's not right. And if you look in the materials, this is made of wood. The lid is made of wood, but the side is made of acrylic. And you might be wondering why we made this choice. And to be honest, it wasn't a choice. It was just because the 3D printer ran out of acrylic halfway through, so we had to rush a laser cut wood lid.
Yeah, so the entire circuit is like a red LED for intensity indicators, like these 8, and also another blue LED inside beneath the lab on chip. For this part, for the indicator well and the RGB sensor above it that with black tape for detecting the well. And every LED needs it's in the breadboard, or you can see over there at the top right image in the middle. Need a resistor to prevent like burnout and limits the current for the test. And after we finish we just started doing the testing today, and so we calculate the calibration curves using after we measure the intensity of known concentrations. We have a known concentration of 250 ppm, 500 ppm, 750 ppm, and 1000 ppm. After calculating the equation by those known concentration, we can reuse it to calculate the ppm of a unknown concentration. And there's actually a problem when we first attempt, because first time we're using positive pressure to pushing the liquid in to make the RGB sensor to sensor the concentration, but then we figure out the positive pressure is going to cause the leaking that's going to stain on the RGB sensor, which causes it constantly reading the exactly same value. So how we fix it is we replace it with a negative pressure, so it stops the leaking, so we can read the accurate value.
Okay, so I'm going to talk about how it really works. As Eric mentioned, there is a blue LED at the bottom of the chip. And the reason it's a blue LED is because the blue light activates the fluorescein, which is the chemical used, and it releases a green glow, which the color sensor actually tracks the intensity of the glow to give us what the concentration is. And the way we determine the concentration is we have 4 initial points, like he also mentioned, 250 all the way to 1000. And we're given, using like empirically, we find the concentration of each of these and then the intensity of the light. So we can match that into a linear regression scale, which is kind of better known as a best fit line, where we can estimate what the intensity, what the concentration would be based on the intensity of the light. And the way our code works is in our Arduino, which I don't have pulled up, we have a bunch of else if statements, and each of these gives you a range of what the possible concentration can be based on the intensity. And like I mentioned, this is from the linear regression.
For timeline, first week we just learn like what we're going to do, and with a lot of laboratory and a lot like expensive and cool machine, and we learn how to use Omshade to build our 3D models and learn how to code. And second week we just start to build our box, and last 3 days we just fix the problems we have, and Christine and Sasha help me a lot, so appreciate it. And that's all.
Thank you guys.
Hi everyone, our team's name is Wiggly Tech and our project is for dry eye disease detection. So before we get into all the technicality and background and stuff, we're going to introduce ourselves. So hi, my name's Natalie. My main role on the team was for chemical engineering and to do the CAD design.
I'm Chelsea. I mainly focus on the software part.
I'm Thomas. I mainly focus on programming the electrical part.
Toyoung, and I mainly focus on 3D design and graphic design.
Okay, yeah, so you guys actually might be wondering about some of the background of dry eye disease and what it actually is. So it occurs when somebody's eye doesn't produce enough tears or they evaporate way too quickly. And current diagnostic tools actually need a lot of like specialized equipment and a lot of time for diagnosis. So our goal was actually to make a more efficient system using microfluidics and electronics to basically detect concentrations of fluorescein, which is a green hue, to tell whether or not somebody has dry eye disease. And then Toyoung will talk about the design.
So before I dove into the actual design, I want you to introduce you to the app, what we call OnShape. And whatever it does is that it's a app that allows you to 3D model, which can be connected to a 3D printer that prints out the shape you wanted. And why I introduce this because for our device, it uses the device called PDMS and it has sensors that cannot be exposed to normal light. So we need to encase in a box like we see here. And for other design choices, if you look closer, you can see that our design actually has elements of Pokemon in it. And we did that because, we named our team after a Pokemon.
Below our poster is a timeline. On the first week, we learned basic stuff, like mainly we had lecture on microfluidic and microfabrication. We also learned how to soldering and the shape on shape. And on the second week, we move on to like mainly about testing and building where we design our housing. And also we tested the PDMS and built our chip so we could run a calibration curve and calculate the fluorescence concentration.
Yeah, and so now I'll be explaining the design of our box and kind of the materials we use. So for the people in the back who might not be able to see, this is the design of our box from the outside, and I'll kind of be explaining the parts. So below that, there's within the box, there's a RGB sensor that basically detects fluorescein, and that's what we use to find the concentration of the random samples. And then there's the main part, which is basically the chip that we do the experimentations on. You guys might not be able to see the print on the chip, but within it, there's basically wells where we basically pump in the liquid. And this is also where the LED blue light will shine on and it'll create the green hue. And this is actually called a PDMS microfluidic chip. So it's basically a gel chip screwed together between two acrylic pieces. And that's how they hold it together. And then our RGB sensor that I said before is connected to Arduino, which connects to the testing and algorithm.
To test our device, we did a separate test for the concentrations 250, 500, 750, and 1000 ppm, which starts for parts per million. And we detect their respective light intensities. And after we got our data points, we use that we use the best fit linear regression to make a calibration curve, which can be used to detect and predict our concentration based on the light intensities detected. And finally, we implemented our equation into the program and the detection algorithms.
On the top right corner is our algorithm, and it's like a code of our project. It could be mainly divided into 3 parts. The first part is where we set up all the LEDs and the color sensor, and we actually tell the Arduino whether it's an input or an output, so it's what's attaching to it, and the code will run exactly what we want. And the second part is where we light up the blue LED and read the green value to calculate the fluorescence concentration, which is our third step. Depending on the amounts of the red LED that lighted up, we know the concentration of the fluorescence, and we can run a calibration curve.
In conclusion, for our final test, we got a concentration of 254 for the unknown solution. And what went well is that our program and the calibration curve worked and gave us a consistent output.
So there are many things that we can improve on. And if you guys take a look at our box carefully, you can see that we adorned it very aesthetically, but not very practical. Like what we can improve on is, focus on the practicality and the device instead of the design, so that we can make the measurements more accurate and better than before, better than what we have now.
Yeah, but overall, we've improved a lot on our technical skill, and I think some of the most important things we've learned is kind of what people experience in industry in this type of field, like biomedical engineering, chemical engineering, and we worked together for 2 weeks, and we didn't have any major fights or anything. We collaborated really well, so I think that's something that we're really proud of. Yeah. Thank you.
Okay, thank you everyone for those amazing presentations. I know I was impressed how well you all were able to articulate both the objective and the challenges you faced throughout the camp the last 2 weeks. So thank you all for that. And hopefully parents, you guys got an idea of what they were doing the past 2 weeks here. So now we're gonna move into the demo and showcase for Rover. So we'll start with the demo for Rover, and we're just gonna take a couple seconds here to set it up, and then we'll let you guys all view it. We'll have each of them go and run the track that we have here, and then we'll go around and see the Lab on a Chip projects as well, and they'll just show you kind of the inside and how everything works in there. Great. Thank you, everyone. Okay, I'll close this quick here. If Ed and Zaria, do you guys want to start setting up the track there? Sure. All right, do we have any volunteers to go first with the demo for the Rover? You guys. Okay. All right, so if you guys want to, feel free to stand up and come around here so you can see the track.
Go, Justin!
Yeah. Anyone wearing red, we may have, well. Okay, can everyone see okay? Okay, great. All right, whenever you guys are ready. What a great first example. Thank you. That was awesome. Thank you guys. All right, who's up next?
Us.
Okay, great.
Comment in your code.
I have proof that
We don't need to show the video. It doesn't work.
No, but like, oh, wait, can we? Oh, what?
Just leave it there.
Brother, it might slip off your strap.
No, it's fine. No, it's fine.
Are you sure?
Oh my fucking god. My cord is off.
You got this, it's okay.
Carol, don't be scared.
It's all up to the Rover now. It was going pretty fast there.
We just
You want to try again?
That or you need to adjust your calculations.
Oh my god. No.
Oh no.
Wow.
I don't know. Paul isn't here. Where's Paul?
Do you want to try from the beginning again?
I'll try. Wait, the IR sensors are too. Faulting the IR. Sorry. Should be fine.
Right there.
Let me see. Let's go one more time.
Carol, don't worry. Why is it like that?
Can you maybe it's too dark.
I'm so confused.
It's Paul's magic touch.
Thank you, Paul. Thank you, Paul. Thank you, Paul. Like, I don't understand. Who hates me? Yeah. Hey, Carol, like,
Wait, I want to.
Okay, don't. Slow and steady. Yeah, Paul,
Start from here.
Paul.
Wait.
Do you want to try one more time from the beginning?
Yeah, why does it look Paul and not me? Like, I don't understand. I made it.
No, let's try one more. Maybe Paul needs to put some good energy in it.
It worked again. Like you proved that it wasn't like.
That's because every time Paul does it, it works. That makes me mad.
Thank you.
Why is Paul so like Paul so
My dad
No.
Paul's the father of all things. Yeah, like he's so experienced.
Or like just him watching is giving it.
Yeah, like you're gonna get bored.
How does
Wait, you know what's a picture?
Yes.
It's a
All good.
It's
gonna work.
All right, thank you guys. I'm just gonna do a picture of the rovers.
Yeah.
Would you guys mind putting them just here on the board? Yeah. Do you mind just putting it down here? Yeah. Thank you. One more. Nice. Thank you.
GG's.
I'm sorry. Sorry.
The chud to be honest.
Chud. Can we get a zoom in on the chart?
Can we get a zoom in shot of the whole face?
Sure. Where's that one?
The green one.
The green one. Okay. Let's do it.
He's a chud. The chud rover. Chud rover.
Okay.
Yay.
Okay. All right. Yeah. Okay. Go. Do you need any more photos? No, we don't have them. Okay, you guys can grab your rovers.
Justin, yours is so well behaved. Like I don't understand.
So for lab on a chip, actually, I'm thinking like, would you guys mind just bringing it over so everyone can see it and just kind of walking us through, letting us see up close how it works? Okay, and I can see a demo if you can show us.
Wait,
Oh, just right here.
Literally just hold on.
I know. No.
Right, I think so. He's gonna give him some support up there.
I think we got it.
Okay, okay.
Put it on the ground. I don't care.
All right.
All right. So does anyone mind like showing the inside and how it works?
Oh wait. Okay. We'll go first.
Okay, thank you, Natalie.
Wait, let me hold this up. Wait, Thomas, can you hold the wire? Okay, so the box is basically 13 by 13 by 13, right? So it's a cube, and we design holes here to stick out the LEDs. These are the things that tell us the concentration. So basically, we explained that on the slides, but you guys might not have been able to see clearly.
Oh,
sorry.
Okay, basically the LEDs tell us the concentration of what's within the chip. It should have a green fluid in it, and when it lights up, there's a blue light emitted from here, which is connected to Arduinos on the bottom. Let me see if I can show you guys. Yeah, so a lot of circuits. And then we have the RGB sensor here, which is connected with wires. And then we basically put it on top of the chip to basically detect the amount of green fluorescein. So we basically have a stand here, and it's 2 platforms. And then, yeah, that's kind of like our brief explanation. Yeah, some accessories. And then the lid to cover it because it needs a completely dark enclosure to detect the right amount of green. Yeah.
That's very cute. Okay. Thank you, guys. Thank you. Okay, the next team want to do something similar? Yeah.
Yeah.
Thank you.
Okay. Sure. Okay. So one thing I forgot to mention during the presentation is our box is a 6 by 6 by 6 inch. It was on the slide, but I just forgot to mention it. The other thing is that the inside paper is red, and you might notice it's different from their glass. And the reason why we have the red paper is because we're trying to detect green light. So red is fine. Blue would have been fine too. But we ran out of black paint, so we used red.
Creative.
Is there anything else?
Let's see. How do you keep your things stable inside?
Oh.
Yeah.
Great question.
Really?
They're not.
Okay, that's the next phase, the next iteration.
Yeah.
Yes. Okay. Okay.
That's
okay. Thank you. Thank you so much. Yeah. Keep C team. Yeah.
First, the lid. We actually paint this according to this.
Oh.
Deep sleep.
That's very good. Whoever painted that did a great job.
Yeah. It's really difficult to take the whole thing out because we have a lot of tape on it. That was a mistake. We didn't design a place to hold our chip, so we have to use a lot of electrical tape. And when we take it out, fine. There was a tape for the blue LED.
Yeah.
And the cable is connected. So this is the second layer, the chip and the pipes. This is our RGB sensor taped on it. And the breadboard, the Arduino. And we have the LEDs in the inside because I don't want to have so many wires randomly being there. That's too annoying for it. So we have some tape fixing them like in groups. This is the RGB sensor group, LED group, and connection group.
Yeah, very good. Wow.
Our box is kind of ugly. No design, just our signatures.
Oh, I like
No,
that.
it's cute.
It's personalized. Yeah, that's great.
Good job.
Yeah, thank you. Thank you, guys. So real quick, before we move into the next phase, we're gonna grab the cables from you guys, any USB cables and batteries that you might have. So if you just want to put those in the back with Ed and Josh back there, just go ahead and hand any cables and batteries. And then you guys are free to keep the designs that you made. So you're free to keep all the parts other than the battery and the cable. You just have to pick which person in your team gets to keep it, which I guess is going to be the hard decision.
Yeah, sure.
Does anyone have any paper?
Mama, 要过来看一下吗？
你要不擦我？
Thank you. Kristen, thank you for your help. I need your cable. I need your cable.
Guys, do not touch it. It's still wet.
Okay.
Thank you. And then at the very end, yeah.
I can fix. That would be great.
Yeah.
Okay.
You painted it, I guess. You have a right
We have many. And where's Carol? Carol. Carol.
We can trade it off. Yeah, I was driving 30 minutes to your house. I was like,
Okay, never mind.
Okay, no.
It's called PDMS. It's kind of like gel, but it like cures everything. You basically put it on top of it, and then the light emits, and then it shows the light. Like it literally works. Sasha, can you like endorse me and say it works? It works. Yeah, we 3D printed it, and then Oyan wanted to paint it, so I let him paint it. It's fine. It's okay. Now we like, we did a random number generator, and I was the one, and it went to 1. So I get to keep it. It was like, this is Carol. Hi. Can we take a picture with the squad? Oh, and Billy, you can join. And Billy.
Yeah, we can join.
Guys, are you keeping this? Wait, I want to put it all on my tips. Like, this is my baby. Like, I literally been working on it. We like 3D design this squad. And we like,
whatever you have.
sure. That's Betty's, but sure.
Betty, can I have this? I mean, I'm gonna watch.
Wait, Betty, like, all your projects. Like, for sure. Well, yeah, wait, Betty, are you sure? Wait, bro, I don't even have the rest of this. I don't even have these.
Wait, are we gonna take the record out? No, I want to take some part of it.
Wait,
No, but he's taking like the chassis and the chassis. Just rip it out.
wait, like, oh, I actually you want the box?
Yes, I want to. Yes, I take the box.
You want the box? Wait, I think I just trying to that.
Oh my god.
I'll keep my best.
Wait, can we take like photos? Wait, tell your mom we're going to the different. Okay. You guys make it so pretty. Okay, it's pretty, but theirs is very like ours is a pink. Yeah.
I don't want it. I have no use for it.
Like, just get it on your phone. Like,
Yes, please. What number?
That's a curve that I had.
Grab one.
And I also did some of the houses.
Wait, what's the biggest problem?
And the cables are at too.
I love it.
Why is Paul like actually
That's why I ran to team with your IR sensors. Everything else I mean, Paul.
Yeah, mine's only Paul is mad too.
Hey, I was also.
And you, wait, you guys, we need to tell us something was Paul.
Last picture of
Paul, we need to take a picture with you. You're magical. Paul, we need to take a picture with you. Let's get some. Paul, my rover fucking hates me. Stop cursing. My rover. Wait, come in. Why? You didn't call. You weren't even on. No, but he took us to the freaking lab. And I saw Among Us version of it. I need someone to Chris, we took a picture for like, Billy. Billy. Where's Billy? Billy. Okay, Billy's going. Okay, we really need him in. Oh, fine. Wait, I'll where's your phone? Why is the live stream? Okay, Paul.
There's quick. Well,
5 people watching the live.
Oh, what if my dad is on? Oh, wait, let's do it. I want to stand next to him.
We'll do it after.
All right, guys, can I get you all to take your seats again? We're gonna move into the next phase. Okay, awesome. Thank you guys. So we have prepared certificates for you guys for completing the camp for this year. So we're going to hand those out. I'm going to ask UA to come up here and help me to pronounce the names and hand out the certificates. And then we also have a little souvenir for you guys to take. So every student is going to get one of these little anteaters. They're called headers. Students actually collect these around campus. They give out stickers, and it's a big deal on campus here at UCI. So we created these for all the students. You may have seen our staff working on them this week. So you guys will all get one of those as well. So let me see if I can play.
All right, the first certificate given to Jiaqi.
Your keychain. That is
All right, great.
You went first.
Next one, award to Poyang. This one is photo. Great. Oh, okay. All right. That's why I work to Qingyi. Yeah. Yeah, the keychain. All right. Next, word to Brian. Where's Brian? Oh, Brian's here. Good. Congratulations.
Congratulations. Your keychain.
All right. Good job. Let me check. I was like, we find a Yeah, you're right, Michael. And Ray, Michael. Yeah. Congratulations. Oh, thanks. Thanks. All right, next over to Thomas. Thomas. All right, congratulations. All right, awarded to William. Yeah. To the side. Congratulations. All right, that's over to Natalie.
Yeah, just one, yeah. Thanks, Kristen!
Congratulations. Oh, you want it? Oh, I'll take it. Okay, I have a problem with that. Oh, Chelsea. Right. Congratulations. Ah, keep it.
Yeah, I don't want the certificate. I just want the
Right. That's awarded to Eric. Eric. Right. Congratulations.
Congratulations. Here's your keychain. Cheat sheet.
Oh, great. Okay, okay. It's award to Amy. Amy, yeah.
Thanks. Thanks.
Right.
Thanks.
Congratulations. All right. That's awarded to Ryan Zhao. All right, congratulations. Oh. Oh, another Ryan. Ryan won. Yeah. Okay. Oh, that's how you think. Okay. Okay. Thank you. Alright. That's awarded to Daniel Chan.
Congratulations. Thank you. I know, like I feel like we did so many already.
That's awarded to Justin.
Congratulations.
I got from the fire.
That's awarded to our student Joshua. Joshua. Oh, Joshua. Hey, congratulations. All right, thank you. All right, next awarded to Caroline. That's awarded to Jen. Congratulations. Right, that's awarded to Allison. Yeah.
Congratulations.
All right. Jeff, double check. All right, that's awarded to Jeff. Yeah. All right. All right, congratulations.
Okay.
Oh, this is, I think it's Lawrence. Lawrence. Okay. You want to get it? Lawrence? All right. All right, so have a photo.
Lawrence.
Lawrence. Great. All right. That's awarded to Lucas. Congratulations.
Congratulations.
All right, good job. All right, that's awarded to another William. William,
Lots of creepy names this
Yeah.
time. Yeah. Thank you. Congratulations.
All right, good job. Oh,
Oh, Darren.
Darren. Awarded to Darren.
I need that. 15 minutes of silence.
Good job, good job.
Wait, will that actually help?
Oh. You guys can see what I like to watch, I guess. I guess they expect you to finish graduation quickly.
Yeah, that's one awarded to Benny. Congratulations. Last one on the list. Give it to Daniel. Daniel. Right. Good job.
Thank you.
Okay.
So I think UA has some words to say to you guys, because some congratulations.
All right. Yeah. Thank you, everyone, be here. I'm Yue, the provost of Franklin Academy, and also the program director of this engineering camp. It's my honor to spend like 2 weeks with our amazing students. We stay together, we study and work together. 2 weeks ago, right? Someone like most of you just come to campus as strangers. You don't know each other. Some of you just here was excited. Some was like nervous. Some of them like wouldn't have no idea what to do, right? So don't have any expectation at all. But today, you're leave with engineering knowledge and skill set. And more than that, I believe you have unforgettable memories. You have a new friendship, right? And most important, I think that you get a deeper understanding how to think and work as an engineer, right? Yeah, I believe. Yeah, and like every day, I believe we have a lot of college, right? We have college level classes. We are lectured by the professor, by the graduate or undergraduate researchers, and we are working very hardly in the lab almost every day. Yeah, so this gives you a lot of idea what engineering should working with. All right. So today we are witness our the result of your hard work, right? So those projects, no matter it's like autonomous rovers project or the lab on chip project, that is like countless hours of working, like hard working and experience and testing in the lab, right? So I think we should give every one of us a round of applause. And I also want to mention that the process, no matter what the result you get, but the process is a good learning that you need to take away. So engineering is a process that you need to ask the right questions, right? So you need to learn from the failure, right? And you need to do a lot of testing and rebuild it and maybe test again, right? So I'm very happy that a lot of students here is actually in this process. In the last two nights, we're working very late night, right? Until 10 p.m. Our mentor helping some of students just keeping doing the code and redesign their maybe chassis or the cat housing. But yeah, so we're facing a lot of failures, right? So like a chassis broke, what we need to do, we redesign it, right? And 3D housing is not fit, right? We need to just send a new job to the 3D printer and do this again, right? So this is how the engineering works, right? All right. Lastly, I want to show my appreciation to the School of Engineering of UCI. Without their help, we cannot make it happen. And seriously, I want to give my deep appreciation to all our good, amazing mentors. They give all the patience, right? A lot of the lot of patience. I know our students have a lot of questions, and also Professor Wu, Kristen. We actually developed the curriculum and the project almost at the beginning of the year, right? So we do a lot of back-end works, make it everything is moving smoothly, and also. Yeah, I want to thank everyone. Your expertise, I think, is a big change to our students in their near future. Let's give another round of applause to our amazing alumni. Also, thank you all the parents. Your shows in this event, I think, is supporting a lot to our students. Thank you.
Thank you, Yue. Thank you for that encouragement for the students. I just wanted to echo what he said and just say that, I recognize all the hard work that you guys put in these last 2 weeks. And I heard, from our staff that you were working late in the lab. I know it's a lot of work, but it really shows in your presentations and your demos today. You guys did an amazing job. I was so impressed with what you showed me today. It really shows that you guys mastered the engineering design process, as Yue said, with that, kind of design, build, test, and iterate until you get it working, right? And you guys did an amazing job of that. Especially as, high school students, we are really impressed. You may already know that we've run this project for our college students, for undergrads here at UCI, and it takes them 10 weeks to complete the project. So you guys did all of that in just 2 weeks, which is no small feat. So you guys should give yourselves a little pat on the back for that. That was amazing. And you guys all have it working in the end. So that is truly, truly impressive. So thank you all for persevering through that. And as you guys said, I just also want to give a huge thank you to our staff in the back there, our TAs and our UAs that worked tirelessly with you guys this week on the ground to get things working. So let's give a round of applause to them. Congratulations, everyone. And like I said, great job. The next thing we're going to do is move into a group photo. So I'd like to get a photo of everyone out in the courtyard here. It's a beautiful, sunny, hot day out there. So we'll try to be quick. And then we'll come back here and grab your things. And then that will conclude our ceremony today. So thank you, everyone.
I really don't care. If you want to Okay, yeah. Sorry. Thank you.